A control system is a systematically arranged set of components, which together act to produce a desired output for a given input. A control system is a systematically arranged set of components which together act to produce the desired output for a given input. The basic representation of a control system is depicted in figure 1. Plant or process, input, output. In control systems, input is also called excitation, output is also called response. This is how a control system is defined. Next I go to types of control system. There are two types: open loop control system and closed loop control system. First one, open loop control system. In an open loop control system, the control action is independent of the output. In an open loop control system, the control action is independent of the system output. What does it mean? This means actuating signal does not contain the component of the output. In an open loop control system, the control action is independent of the system output. This means actuating signal does not contain the component of the output. The general configuration of an open loop control system is a short form. C bar S means control system, is as shown in figure 1. See, input, also called as command. This input is given to a controller. Which produces the actuating signal. Actuating signals are also called as reference input. Actuating signal also called reference input. This actuating signal is given to the plant. Using this actuating signal, the plant produces the output. This is the general block diagram of an open loop control system. This I call figure number 1. Now let us take an example of an open loop control system. Example is voltage control of a DC generator. Voltage control of a DC generator. Let me put the circuit diagram first. We have got a potential divider. The input voltage, the potential divider is VI. The output of the potential divider is VR. Right? This potential divider output is given to the field of a separately excited DC generator. This is the field winding of separately excited DC generator. The voltage across this winding is Vf. The voltage across this is Vf. In fact, the field current is If. Making use of this reference voltage, the DC generator produces a open circuit voltage Eg. This is the armature resistance Ra, and RL represents the load. Which is a variable. The voltage across the load is VL, and this is the armature current Ia. The block diagram of this circuit is as shown below. The block diagram representation for the above circuit is as shown below. The voltage VI is converted into VR. VR is less than VI by the potential divider. This is the potential divider. The output of the potential divider is VR. Making use of this VR, the generator produces a voltage, open circuit voltage Eg. From Eg, we shall subtract. This is the symbol of a summer. This is plus. This is minus. We subtract the voltage drop Ia Ra. From Eg, if you subtract the voltage drop Ia Ra, you get VL. Now, if you see this block diagram, VR is independent of VL. Therefore, it is an open loop control system. We have taken this example in which we have taken a separately excited voltage generator which converts the reference voltage VR into an open circuit voltage Eg. From Eg, if you subtract Ia Ra, the voltage drop across the armature resistance, you get the load voltage VL. If you look at this block diagram, VR, the reference voltage, is independent of the output voltage VL. Therefore, this circuit diagram represents an open loop control system. The reference voltage the reference voltage VR is independent of the load voltage or output voltage VL. Hence this you call figure number 1, this you call figure number 2. Hence figure 1 I have already written here. This you call figure number 2. This is figure number 3. Hence, figure 2 represents an open loop control system. Open loop control system. This is the symbol of a summer. Some people, instead of using this symbol, they use this symbol, plus, minus. This is the alternate symbol of S summer. Both the symbols are in vogue. This is another symbol of summer. So, an open loop control system I have explained. Then I will go to a closed loop control system. Closed loop control system. In a closed loop control system, the control action is dependent on the system output. In other words, the actuating signal has a component of the output. A general block diagram representation of a closed loop control system is as shown in figure number 1. This is input or command. This is controller. Output of the controller is called reference input. In the previous case, reference input was same as actuating signal. This is summer. It is also called error detector. This is plus, this is minus. Output of this error, this is called error detector. The output of the error detector is called actuating signal. The actuating signal drives the plant. This is the output of the plant. Here we have got a feedback network. feedback network or I write feedback element. It senses the output and gives out a feedback signal. This is the general configuration of a closed loop system. Activating signal equals reference input minus feedback signal. Feedback signal contains a part of the output. Therefore, activating signal has a component of the output. That is what I have explained here. In a closed loop control system, the control action is dependent on the system output. In other words, the activating signal has a component of the output. I again repeat with respect to this figure. Activating signal is equal to reference input minus feedback signal. Feedback signal can be the entire output or a part of the output. Therefore, activating signal contains a component of the output. Let me give an example. Example, voltage control of a DC generator. This is the potential divider. Input to the potential divider is VI. Output to the potential divider is VR. This output drives the excitation of a field generator, of a DC generator. This is a field winding. This is the armature. Let me write a figure and explain to you. This is the armature, plus minus. Open circuit voltage is EA or EG. This is the general block diagram. It is used for controlling voltage of a DC generator. There is feedback action here. How that feedback action takes place, let me explain with the help of a block diagram. This I call figure number 1. Figure 1 depicts a closed loop control system depicts a closed loop control system. The block diagram representation of figure 1 is as shown in figure 2. VI is the input voltage to a potential divider. Potential divider converts VI into a voltage VR, which is less than VR. Correct. Then if you apply KVL to this loop, this is plus minus. You apply KVL. If you apply KVL, what you get? Minus VR to this loop, minus VR plus VF plus V2 equal to 0. This implies Vf is equal to Vr minus V2. So from Vr, if you subtract V2, you are going to get Vf. Look at this equation. Vr minus V2 is equal to Vf. So Vr minus V2 is equal to Vf. Vf is converted into Eg by this generator. This is generator. This is Eg. From Eg, if you subtract IaRa drop, armature voltage drop, you get VL. So VL into R2, VL into R2 divided by R1 plus R2 is equal to V2. Potential divider action. So VL, this is the feedback network. This is the feedback network. What is that ratio? R2 divided by R1 plus R2. Input to this network is VL. VL multiplied by R2 divided by R1 plus R2 gives you V2. This is general configuration of this side. This is the block diagram representation of figure 1. Vf is the actuating signal. Vf is the actuating signal equal to what? Equal to Vr minus V2. If V2. And what is V2? What is V2? V2 is VL into R2 divided by R1 plus R2. If VL increases, Vf decreases so that the output is maintained constant. Conversely speaking, if VL decreases, Vf increases so that VL is restored back to its reference value. That means there is a corrective action in a closed loop system. If VL increases, Vf decreases. Or if VL decreases, Vf increases. That is, output VL is maintained constant. In a closed loop system. Closed loop system is also called a negative feedback system. Negative feedback because of this minus sign. Negative feedback system. If VL increases, Vf decreases, or if VL decreases, Vf increases. That is, output VL is maintained constant in a closed loop system. So what is important is actuating signal has a component of the output. What is that component? VL into R2 divided by R1 plus R2. Next, there are several examples. You can go through these examples in the book that I have written, Control Systems by myself and my teacher, Dr. Channa Venkatesh. Please go through the book. There are many more examples of open loop and closed loop systems. Next, let me compare open loop and closed loop systems. Open loop versus closed loop systems. open loop system, closed loop system. Construction and design of an open loop system is simple, hence cheap. Complicated closed loop system design is complicated and hence more expensive. So I am going to write first point: construction and design. Construction and design are simple. Construction and design are simple. Hence less expensive. For a closed loop system, complicated design, more expensive. Complicated design and hence more expensive. Second one, generally stability is not a problem. So open loop systems are generally stable. Designer should be careful because there is a tendency for the system to become unstable. I am going to write here: designer should be careful since closed loop control system, CLCS means closed loop control system, has a tendency to become unstable. Third one, less accurate and less reliable. More accurate, highly accurate and highly reliable. The actuating signal is independent of the output. The actuating signal has a component of the output. Fifth point, sensitive to disturbances. Insensitive to disturbances. Sixth one, small bandwidth. Larger bandwidth. Last point is non-linearities affect the system response. Effect of non-linearities is restricted is restricted to a large extent. Is restricted to a large extent. Is restricted to a large extent on the system response. On the system response. In the examination, sometimes they ask, what are the advantages of closed loop systems? Then also you can write this. Or they may ask what are the differences between open loop and closed loop systems. These 7 points are very critical. Memorize them and write it in the examination. Please don't think control systems is only theory. Now the actual control systems will start. It is highly analytical in nature. Next topic is mechanical translation and rotational systems. Mechanical translation and rotational systems. Rotational systems. Mechanical systems obey Newton's law. What is Newton's law? The sum of applied forces must be equal to sum of reactive forces. This is called Newton's law. And Newton's law is obeyed by mechanical systems. So I write here mechanical systems. Mechanical systems obey Newton's law. Obey Newton's law. What is Newton's law? What is Newton's law? The sum of applied forces must be equal to sum of reactive forces. Sum of reactive forces. Sum of reactive forces. Now I'll take the basic elements of a mechanical translation system. So first I'll take mechanical translation system. In that, first one is mass. First component is mass. Let us assume a mass m. Let us assume a mass m subjected to a force f of t. The displacement of the mass is x of t. So I am going to say, let us apply a force f of t to mass m. The resulting displacement is x of t. What is the reactive force? Reactive force is mass into acceleration. Mass is in kgs. Mass is in kgs. Displacement is in meters. And force is in newtons. So, let us assume mass m is subjected to a force f of t. The resulting displacement is x of t. The reactive force is f of t is equal to m into d square x of t by dt square, and unit of force is newtons. So this is nothing but force f of t, reactive force f of t is equal to mass into acceleration. Next element I am going to take is spring. Next translation element I am going to take is spring. Spring. Let us take a spring having stiffness K, newtons per meter. These are the ends of the spring denoted by C and D. C has got a displacement of position equal to xc. The end D has got a displacement of position equal to xd. These positions are measured with respect to their equilibrium positions. So I am going to write now the reactive force. The reactive force in this case is given by Fk of t is equal to k into xc minus xd, where xc is equal to position of the point C. xd is equal to position or displacement of the point D. K is equal to stiffness or elastance of the spring in newtons per meter. X in position of the point C, unit of xc is meters, unit of xd is meters, force F of t is in newtons. So the reactive force Fk of t depends on the relative displacement of the points C and D. xc is equal to position of the point C, xd is equal to position of the point C. These positions are with respect to their equilibrium positions. Correct? This is how a spring is done. If position C is fixed, if the end is fixed, then xc becomes 0 and force will be k into minus x of d. When d is fixed, then xd will be 0 and Fk of t will be k into xc. I am going to write here, if end D is stationary, then the reactive force Fk of t is equal to k into xc minus 0 is equal to k into x. Unit of k is newtons per meter, unit of x is meters, newtons per meter into meter gives you newtons. This is how a spring is dealt with. So you should remember all the reactive force equations. Third element is damper. A damper is nothing but shock absorber which you will see in any automobile. This is the basic symbol of a damper. This end is E, the other end is F. The reactive force, this is third element, is damper or dashpot. In this case, the reactive force is given by Fb of t is equal to B into dxe by dt minus dxf by dt, where x is equal to position of the end C or point C. xf is equal to Position of the end F. Both are in meters. B is equal to coefficient of viscous friction. Coefficient of viscous friction in newtons per meter per second. Look at this. dxv by dt and dxf by dt are the unit meters per second. And unit of D is newtons per meters per second. Newtons per meters per second into meters per second will give you newtons. The unit of the reactive force Sp of T is also newtons. If NE is end F is stationary, then dxf by dt becomes equal to 0 and Sp of T will be just B into dxc of T by dt. I am going to write it here. If end F is stationary, then the reactive force Fb of T is equal to B into dxc by dt minus 0 equals B into dxc by dt, so many newtons. So there are three translation elements. Then there are three rotational elements. Rotational elements I will consider one by one now. Mechanical rotational systems. First one, moment of inertia. This is the moment of inertia represented in kg meter square. The input for moment of inertia, instead of force it is torque, output is theta of t. Input is torque, the role of force is taken over by torque and the role of displacement is taken over by theta. So symbolically I represent in this manner. J having endpoints A and B. Unit of J is what? Kg meter square. What is the reactive torque equation? The reactive torque equation is Tj is equal to J into d square theta of T by dt square. That means theta is the net moment of inertia is applied with a torque. Is the applied torque T of T. The resulting displacement is theta of T. When you subject the moment of inertia to a torque T of T, the resulting displacement is theta of T. Correct? Tj of T. Unit of torque is what? Newton meters. Unit of J is what? Kg meter square. Acceleration is in what? Meters. Instead of kg meter square. Unit of acceleration is what? Radians per. Unit of velocity is radians per second. This is d square theta by dt square is radians per second square. That means moment of inertia multiplied by angular acceleration results in the reactive torque Tj of T. Second element is spring. What is important is force is replaced by torque, linear displacement x of t is replaced by angular displacement theta of t spring. Okay. The endpoints are C and D. What is reactive torque here? The reactive torque is T K of T is equal to B into theta C minus theta. Rho of x is taken over by theta. Unit of torque is Newton meters. B is called K. Unit of K is what? Unit of K is Newton meters per radian. Theta C minus theta D is in what? Theta C minus theta D is in radians. Newton meters per radian into radian gives Newton meters. In the case of translation system, unit of K was newtons per meter. Here it is Newton meters per radian. Third element is damper. What is reactive force? The reactive torque. Whenever we deal with rotational system, we must use torque. Whenever we deal with translation systems, we have to use force. The reactive torque is given by TB of T is equal to B into d theta E by dt minus d theta F by dt. Unit of this is Newton meters. That means all linear quantities or translation quantities are replaced by angular quantities. Force is replaced by torque. With this, we will do problems in the next class. Thank you.